Okay, so let's actually start. Uh, there'll be some mathematical parts, but probably we'll try to skip it. uh, so far what we have talked about Markov decision processes, and then state action value functions, and mostly, in fact, the last few minutes that I was motivating it, I was thinking in terms of a table, right? In fact, a 5 cross 2 table in the running example. Now, such tabular forms are not kind of useful, not very useful in anything beyond a toy problem in today's world, at least. So we have to move beyond that. For example, this is just a picture of, on the left side you see a world, as in the environment, where you can look at the coordinate of your, where you are. Okay, so you can, your state is going to be just xy coordinate of where you are. Okay, on the, and then the actions are still the same: forward, backward, left, right, and there's some rewards. Okay, so that's a description. But you could also have a description where your state is just the camera view in front of the robot. Okay, from that camera view, maybe you can deduce that, oh, you are in cell, you are in some xy coordinate if you want. Okay, but in general you will have, you will have such a high resolution, not high resolution, high dimensional state. Okay, and so you'll not maintain a table where every time the camera is looking at, moves one step forward, a lot of pixels change. That's like again, like 100 cross 100 numbers changing or something like that. So in this case, clearly something else is needed. Okay, so in the sense that you can't really maintain a table, that's what I want to get to with this slide. Okay, you can't always work with a table or update that we were seeing a few minutes ago. So the natural recipe is, then, since I don't want to have a table, but I want a function, which is a q value function. What does the function do? Given a state and an action, it produces a number, right? That's what a q function is. Or given a state, produce, and there are, let's say, two actions, then it produces two numbers. It goes from one state representation, whatever vector or symbol representation, to two numbers. Okay, so that's the function I want, and I can use any function, and we'll see that we'll use a deep network to represent such a function. Okay, so in particular, we can use a deep network to represent both the value function. In this case, as I said, this q of s comma a, this q is going to be a function of all these weights comma biases type of a situation, with those as the parameters. Or you can directly have policy, pi of s can also be parameterized by a bunch of weights and biases. Okay, the policy itself is a function, right? Going from states to actions. Let's say there are only 4 actions. So every state, if it's a camera image, you're just saying, oh, given this camera image, tell me which of the 4 actions is what I need to do. So it's the 4 actions are like 4 labels. Okay. Although it's not a supervised learning problem, but you just, think in terms of a function. It's a function which can go from a camera image to one of the 4 labels: left, right, um, north, south, or the model. Okay, so here's the picture, right? So I mean, the picture is what we're trying to show is that S and A can be an input. Then we want to produce a scalar value, which is the value at the state and action pair. And so that's like a regression problem. So state and actions could be high dimensional. If the state itself could be an image, for example, and this will be some number you want to output, and you want to tune the weights. In this case, these W's are going to be what you tune. Okay, you learn. Okay, instead of the entries of the matrix, what you're learning now is going to be these the W parameters. Okay, that's all. That's what's changed. Or you can have a slightly different representation where you are saying, oh, given the state, tell me if there, let's say there are 4 actions. For each of the 4 actions, what's going to be the q value? Okay, so that will be 4 numbers. Okay. um, so as I said, you can use any function approximate function, any function actually, linear function, decision trees, neural networks, or even nearest neighbor methods to work with this. Okay. So why are we doing this? Okay, so from this slide, the only takeaway is scalability. This slide and the previous that maze type of situation is that you can't just work with states cross actions type of a matrix, so, with type matrices. Okay. Um, so Okay, so let's do a warm-up example, which is that let's say I already told you. So this example is a very simple example where we already know the q. Let's fix pi. Okay, so there's some policy that's already known. So there's no learning going on here, except uh, we know pi, we know q pi as well. As in for every state comma action pair, we already know q pi. Okay. Now what we want to learn, so the learning part is just that, oh, what if instead of this q pi that which I know for every state action, I just want to know, tell me a w which approximates this function. Okay, so all I'm saying is I already know this q pi function for every state comma pair. I can tell you what the q value is, for example, but I want you to only look at this function class, maybe linear functions, from which means that what is the best linear function approximator which approximates really well this q pi. Okay, so the one in the blue is already known. Okay, those are the targets or fixed values. Okay, what you want to optimize for is the best parameter. If it's a linear function class, this w is like a, but it's like a beta coefficient, right? It's a vector. And here is a loss, which is just the square loss. Okay, it's just for every pair of state action pair under this policy. Okay, that's reachable by this policy. uh, you just take an average. Okay, so that's just some sort of an empirical average. Okay, so here it's not really so I'm not talking about q learning and so on yet. All I'm saying is if you know the true q, you just want to approximate it with a function which is parameterized by a parameter w. Then this would be like a square loss function approximation uh, um, estimation problem. Okay, so the approximation parameter, sorry, the approximating functions parameter w is what you want to figure out. So for every w, this is a score. You want to kind of find the w which minimizes the score. Okay, that's the example that I want to drive here. So how do you find uh, a w? You can do gradient descent. You have least squares loss. Take the gradient. Okay, so gradient would be just the argument itself plus times the gradient of the thing which involves w. Okay, so that's the, if you have anything squared loss type of a thing, you'll have the square loss without the square times the gradient of the function which is the function of w in this case. Okay, how many of you did not follow this star step? It's fine. Okay. Uh, yeah, and then that one half and all is gone, so it's not very important. So and then the update, once you know the gradient with respect to the loss, so this is the gradient with respect to the loss. Okay, is some, if w is 10 dimensional, this is a 10 dimensional vector. Now the change in w, which is wt plus 1, is wt minus alpha times or plus alpha times something like this. Okay, that is your choice. uh, Depending on gradient ascent or descent, appropriately you choose do this. Okay, so that's it. This is the gradient update step. If you know the gradient, so the gradient was just copied from here to here. This thing in the new right hand side of the numerator is just literally copied here, and delta w just means w old, sorry, w new minus w old. Okay, it's like saying w new is equal to w old minus alpha times gradient. Okay, any questions? Maybe I should put a minus here so that somebody's not confused. It's basically w new is w old minus alpha times that gradient of w, the thing in the there should be a minus here. Yeah, there is a minus on the left side. Yeah. Yeah, so that's why I think there was no minus here. Good point. So let me just correct it back to plus there. And yeah. Yeah. Okay, so yeah, here in this slide is the same expression with linear functions. If q's are linear functions like this, then how does the gradient look like? But let's skip that. Um, okay, so Next, what we're going to do is now talk about Q learning. Okay, so previously was just a function approximation for any fixed target function. Okay, so this is just the update equation for Q learning, and we actually know Q learning is inspired from Bellman optimality equation. So this is Bellman optimality equation written in a form where left hand side and right hand side are on the same side. Okay, so that's the expectation of left hand side minus right hand side is equal to 0. Okay, and from this you can actually kind of intuitively think about if I had an approximation. So there are two things I'm going to do. Um, if I'm going to approximate, so I'm going to approximate this Q's, okay, with function approximator. So both will have an additional parameter W, and those are the ones I'm going to learn, okay. And also, that's the function approximation part. But because of this expression, I can think of trying to minimize the difference between these two terms, okay, which means this term and this term, as in some sort of a squared loss between these two terms is what I want to minimize. Okay. So in fact, if the square loss is 0, then this expectation is equal to 0, which is what is given there. So all I'm saying is at intuition level, the term RT plus 1 plus gamma max should be close to Q, right? So that's what we want. And we want to tune W so that we can get these two numbers to be close to each other. Okay. But there's W on both sides, so which may lead to some complications, but we'll see soon. Okay. So what I'm trying to say is that first we introduce W, which is the parameter of this now functions now, which is in our tables. And the second thing is because of Bellman optimality equation, what we can say is that we basically want to minimize the kind of this is the TD target or the approximation to the return random variable should be close to Q. Okay. So W has to be tuned such that this number is close to this number. That's what we want intuitively. Okay. So actually, yeah, actually, we're gonna spend some more time on this, so it will be more clearer. So, but in between, I'm gonna just describe a few things which you already know, which is the success of function approximation. So this Atari breakout that we've been seeing for some time is based on CNNs. Actually, the function approximator is a CNN. So for many of, in fact, for all these 50 odd games, the function approximator used was a CNN. Okay, CNN, which we have. In fact, I'll probably have a picture pretty soon. Um, um, yeah. So, but there will be two aspects of the problem which kind of make it more complicated than regular supervised learning. One is that the data is not IID, so you want to train this function. In this case, it's going to be a CNN for the Atari games. The data is not IID, so not like images of cat and images of dog and dog. It's going to be this screenshots and actions and rewards. And also the policy, or in this case whatever the values may be too sensitive to the action choice. Okay, so there is some because there is a you're trying to um, yeah, because there's a max operation, basically I wanted to say, because there's a max operation going on with some discrete choices in your targets, for example, that may cause some issues, but we'll kind of get into it again soon. So let me talk about the DQN itself, which is that CNN part. So in particular, what we're going to do in the next 45 minutes or 40 minutes is spend 15 minutes on DQN and 20 minutes on AlphaGo 0. Okay. So these are somewhat older technologies now. So let's start with DQN. And so why deep representations? We have already spent 6 lectures on deep learning, so this should be a kind of recap for you guys. Basically, because in 2014, by 2014, we had like less than 7% error, which is like very comparable to humans or beats humans in image classification problem. Okay, but I think it's a slightly different, modified, definition of error. Okay. Um, And instead of stack where you do a lot of engineering, feature engineering, you would here we are kind of capturing some structural properties of the images directly using this column operations and so on, and a lot of nonlinearity in the picture. Okay. Um, and in particular DQNs use CNN, so that's why I'm kind of recapping what CNNs are. CNNs capture two properties: local connections and pooling, right? Local connections basically via weight sharing, so uh, there is a spatial aspect that is being captured, and pooling is basically kind of translation invariance, because it's coarsening things, but at the same time it just means that whether some important feature is at the top right or top left or bottom right, it doesn't matter. Ultimately it will be captured, okay, if it's a important feature that got detected, is like that. Okay. And so let's figure out some details about this agent that plays Atari. So Atari, the rules of the game are unknown. Okay. So the agent doesn't know the rules of the game. So in this case, the script P and script R are missing, basically. What you get to observe is the score change. So that's the little r's, or the actual samples, and the agent has to learn directly from interactive gameplay. Okay. And the agent can literally does the same actions that you can do with the Atari joystick. So I think in this case there are 16 or 18 actions, and observations are going to be the same observations that humans see. Okay. In particular, it's going to be like 4 frames or something, 4 images of this each screen at a certain frequency. Um, so DQN uses CNN as a function approximator, and we'll see, and while trying to see how Q-learning gets changed when you use this function approximator in DQN, we'll talk about two tricks. One is called um, um, target freezing or batch optimization. Okay, target freezing, and the second trick is called experience replay. Okay, so I guess this batch part is the experience replay part, and freezing the targets is the second property. So we'll see. I mean, so these are two things I want to highlight when we bring. So far we've seen Q learning as some update equation. We're going to change it to some sort of a supervised learning type style problem, and that will have these two additional features. Okay, something called experience replay and something called freezing targets. Okay. So what the CNN itself looks like is like this. It has basically two con and one fully connected layer. Um, Actually, two fully connected layers. So it's a pretty short network. Okay, so even ResNet 18 has 18 layers. So this is a very small network, um, and its input is a stack of 4 previous frames of the game screen. Okay, and and there are some 18 odd joystick moves that you can do. Okay, all the pause to delete to left right and all that stuff, and all special moves and all that. And uh, and uh, as I said, there's going to be two key important things. One is called experience replay, and the second thing is called fixing Q targets. So let's go back to Q learning. In Q learning, let's say at any given point of time, now instead of a Q table, we'll have a Q function approximator, which means that we already let's assume that we have a CNN. Okay, we'll take an action according to the epsilon greedy policy, which just means that we see the screen now. Okay, we pass that through the CNN, the currently trained CNN, and the trained CNN will say, oh, these are the Q values for the 18 different actions. Okay, whichever action has the highest Q value, you play that with probability 1 minus epsilon, or pick a random action with probability epsilon. Okay, then what you do is you were at state ST, you took that action AT, you observed some score change potentially, and when you got new screens or new frames. Okay. So this data, this 4 tuple sequence is stored in what is called a replay memory D. Okay, it's just a memory. So just think of it as keep all 4 tuples are being plugged into some database basically, or a row in a CSV file or something. And then what we'll actually do is sample a mini batch from this experience replay replay memory script D. Okay. So now because I got a sample, um, let's call it SAR S prime. That's just one sample, but in general I'll have a mini batch. What I'm going to do is with that mini batch, I'm going to compute targets. Okay. So what are these targets going to be? It's going to be R. So let's say if this was a sample, one sample, then I'll have a target which is going to be R plus max over A prime of whatever Q I have of S prime, um, comma A prime. Okay, I shouldn't have put bracket close there, but W. W is that weights of the network. Okay, so this is called a target. So I'm going to compute these Q learning targets, but I'm going to compute it with respect to W minus. Okay, and that's what I'm calling it as old fixed parameters. Okay, uh, these are called fixed Q targets. Okay, so I have the CNN, but I also have another CNN, okay, with W minus as the weights, whose weights I'm not updating. Okay, think of it as like uh, you know, I need to keep updating the weights of my Q network. That's the whole point of Q learning, right? But what I'm going to do is every maybe 1,000 rounds, I'll kind of make a clone and never update it till 1,000 rounds, and then after 1,000 rounds, make a clone of the current Q network and keep it. Okay, so that clone is what I'm calling as W minus, has the parameters W minus, and with those W minus, I'm gonna get what are these called? These are called targets. Let's call it targets T. Okay, and okay, that's what this thing was, targets T. Okay, so you don't have to look at the whole expression, but just call it T. Okay, and then I sampled this mini batch, right? So I sampled a mini batch, so I got a target T number for each sample from the mini batch, and so I'm gonna have a square loss. So T minus Q of S comma A at the current weights. So current CNN, current function approximator, squared loss, and now I want to find better weights. Okay, so it's just a regression problem, CNN regression problem, where I need to change the weights of the CNN to minimize this uh, regression loss function, square loss function. So don't worry about this expression, call it T, okay? Because we just completed last slide. That's it. So how do you optimize for that? You can do any variation of first order family, like Adam optimizer or whatever floats your boat. So let's look at it again from a pictorial perspective. Okay. So what's happening is you have a Q, which is a function approximated. So that's why it has a parameter theta. Okay. If you had the Q, you would always figure out what is the best thing to do is to always if you had the Q star, the best thing to do always is to take an argmax, be greedy with respect to the Q star. Okay. But you can always do exploration. That's what in Q learning you can do. With 1 minus epsilon, you take the greedy. With epsilon, you take a random action. Okay. Send it to the environment. The environment says, "Oh, you took this action. I'll tell you what the next state is." Okay. Sorry, I'll tell you. Sorry, what the state is, and then this guy telling me what the action is. Okay. And then given that action, I'm going to tell you what the reward you got and what's the next state. Okay, S prime. Okay. So in that state S that I told you, you told me some action A, and therefore here is the reward, here is the next state. Okay, that's a 4 tuple. That 4 tuple is being currently stored in replay memory. Okay, and then from replay memory, I'm gonna keep training this Q network every round. Essentially, the way I'm gonna do it is this guy will always will have many such tuples because it's kind of accumulating over and over again. The replay memory is gonna, its role is to somehow accumulate these tuples, but somehow break the non-iodiness of the data. Okay, which means that if I see SA or S prime, the next guy will be S prime, some A prime. So there'll be some common state. I mean, there's a particular trajectory, then you know exactly. Like if you saw a certain screen of bricks being broken, let's say breakout, then two screens later you'll probably have almost the same screen, and 10 screens later also you'll probably have the same screen. So you don't want to have the same data. Okay, so that's why replay memory, from which I'm going to subsample a mini batch, is going to break that dependence across observations. And from the replay memory, I'm going to collect, let's say, a subsample. A subsample. Let's say in that subsample, one tuple is SA S prime R. Okay. Then what I'm going to do is S prime and R are going to give me the targets. Okay. How do I get the target? There's a this target queue network which is using the old weights W minus, or weights that are not always updated often. Okay. Takes S prime, takes A prime is just the max of that. So the old weights here is, we're calling it theta minus. That plus R is the target, and then SA's prediction is the prediction, and then the difference between those two is the square loss. You want to change the theta such that the square loss is small. Okay, so that's the gradient update. Okay. Any questions about this? So there are two tricks introduced. One is replay memory, and the other one is this target or frozen network. Okay, this is a trick one. This is trick two. Good question. So yeah, actually maybe actually this is a good point. So let's say there was no target Q network. Okay, this is instead of W minus, I'm actually also it's just WI itself, which means that I can optimize it. Now it's actually a more complicated problem, right? It's not even I have to optimize for W, where W appears in both this term and this term. Okay, so it turns out that if you have that, then it's more unstable to optimize for W. Okay. So it's a very simple explanation, saying that okay, let's fix this as not being an argument of the decision variable W that we want to change, so that at least it looks like a canonical supervised learning problem. With square loss. Otherwise, if you make this, I mean, if you remove this W minus, then there's the decision variable is entering two terms of the objective, and there's also nonlinearity here, which is not good. So that optimization problem, ideally you would do that, but that's kind of messy. Yeah.
Looking back to the slides, you have that note about how policy value may be too sensitive to action choice, where you kind of get is this target network and the other network, is that one way to combat that?
Yes. Yeah. So if you make this a function, if this is the actual variable itself, then yeah. So there is this max operation which is gonna influence this. If you call this a target, I mean this is the terminology target comes from like what's it? It's been there from before. So we have been using temporal difference, the target minus um, previous key values, the temporal difference error, and so on. Yeah. But that instability comes from this nonlinearity and this target value is changing. If you because there's a max operation going on, but it's slightly different W value, the max over A could be vastly different. Because it's now a different network, and so Q of the action that maximizes and the Q value at that action maximizing for a certain W has nothing to do with a slightly different W, the Q value maximizing action as well. So there is some nonlinearity here. It's a very hand wavy argument, but so they have figured out that these two are just engineering fixes. By the way, there is nothing extremely principled here. The most principal stuff is what we studied in the first part, which is the Q learning, that it works. Okay, and there are many other algorithms like that which work. But the moment you do function approximation, many of these algorithms don't work. Okay, and so the tricks that we're seeing here, experience replay and fixed Q targets, are just two engineering tricks.
Create this targets in a network by
Yeah.
cloning the initial network, like
Few times, like clone every 1,000 rounds or 10,000 rounds or
it
something.
is a kind of a self-improving network which is comparing itself to
Yeah, the copied weights are just to keep things stable. Okay, the target stable so that the supervised learning problem is not a messy problem. Self play and stuff, self improving, I don't know, but self play we'll get to pretty soon. Okay, which is a different technique. Um, so here is just showing on the x-axis different Atari games, and showing that there are some games like Breakout where uh, the agent is able to play 1300% better than an average human. Okay, so this is like way better than, um, and there are a lot of games where they don't play well. Okay, so they are it's not a silver bullet. So by the way, for all this, it's the same architecture. It's the same two CNN, two fully connected layer network, uh, trained from scratch. So, but it took a long time to train these guys. But it's trained on each game separately from scratch. So here they just this is a figure from their Nature paper from 2016. So you can have a look at it when you have time. Okay. And here they are doing an ablation study, and it's kind of useful for you also to do whenever you introduce a new trick. So when there is no that replay memory, and when there is no that what is it called, fixed targets of freezing, then there is some performance that the Q learning algorithm is achieving. Okay, like 0.33 for breakout. That is what we've been seeing at the brick breaking thing. 3. Now from 3, no replay memory, but the moment you're using freezing, the W minus stuff, you already got from 3 to 10. Okay, so 3x more average, uh, rewards being collected, and now you do the regular Q learning, no W minus, but no replay memory. You actually went from 3 to 40. Okay, so they're just looking at, oh, from here, if I just add fixed Q, this is the delta. From here, if I just change to replay memory, I get this much delta. If I now apply both, it's this much delta. Okay, so this is the final result that they claim. So you have to show the net effect. Each individual effect does contribute, non-trivially is what you want to show. Okay, so let's drop this. There's some parallelization aspect here. Uh, okay, so in the next few minutes, let's look at AlphaGo 0. Okay, and in fact, AlphaGo 0 is a much simpler problem. In the sense of, I mean, other than the computational problem, the problem that we're going to talk about next is in the domain of games as well, but now it's completely deterministic. Okay, here there is nothing unknown. It's not clear. Everything is known except that playing that game is difficult, even if everything is known. In this case, when I say everything is known, the rules are known here. In Breakout, the agent did not know that the physics of the game, for example. Okay, so so what we're going to specifically talk about is this a particular version of uh, um, software. I think AlphaGo 0 is the name, which defeated the world number one player at that time, 4-1. So what is the game of Go? How many of you know already what is the game of Go? So 3, 2, no. So it's a board game. It's basically there are two players, black and white, and each player's objective is to capture as much territory as possible. So this is like a territory captured by the white player because, I mean, so in this example, this is a territory captured by the white player. This is a territory captured by the black player, for example. Or it doesn't have to include boundaries like this. You could have a white player capturing a territory right all around the black player, for example. Okay, like here, if there is white here and here, then I think the game is over. Something like that. I don't know.
If it really did capture all the black pieces, then yes.
Yeah. So if you circle around completely your opponent's pieces, then you have captured their territory, right? Um, so anyway, it's just so at every so board positions are some things like this, and you just have to your move is to figure out, oh, if you're a black player, where should you place your next stone? Okay, so there's no difference between stones. There's no king, rook, and all that stuff which you see in chess, for example. So that's the game. Okay, so someday maybe we should play. So why the game of Go, and why 2016 or now was an interesting time when Google did something interesting, is that so before 2016, RL based agents, reinforcement learning based agents, had achieved really good performance on several other games. Okay, so this is just RL based programs, and these are different games: Go, poker, Scrabble, uh, backgammon, all these guys. And on Go, there was the level was Grandmaster level, which I think in Go hierarchy, I think it's probably not the highest. Uh, so that was achieved by some games, but they are on smaller boards. Okay, so Mogo is on was a software for a much smaller board. Okay, the standard board size is 19 cross 19. So anyway, so that was the situation, and that's why it was significant to kind of do much better here. Okay, reach superhuman performance, and they have already now beaten the best superhuman there. Okay, so best human there. Sorry. Um, so before we get into the engineering tricks, in this case, just like in DQN, the two engineering tricks were experience replay and freezing the targets. Okay. Here, it's a game of Go. The rules are known. So you may be wondering what is the use of RL here. To kind of understand that, I'm going to talk about a specific problem called the forward search problem. Okay. So, uh, so So RL is what I've been telling much of the time. But when you have the models, as I said, the reward process and the script P process, the transition probability, the problem is sometimes also referred to as a planning problem. Okay. So if you already know the script P and the script R, the problem to solve, as I said, is just an offline problem or an optimization problem. I kept saying that it's just it's another name to say that same thing is that it's a planning problem. Okay, it's not a learning problem, but just the planning problem because everything is there's nothing to be learned. Okay, uh, and the forward search problem is a specific planning problem where we don't want to learn. So where we don't want to solve for pi. Pi is the policy which says in every state what to do. That's not what we want to do. It's a very simple planning problem where we just want to know in the current state what is the best thing to do. Okay, so I don't want to know pi, which is the function which maps from every state what action to do. I just want to know in this current state what action to do. Okay, so I don't care. So for example, the question will be, oh, I'm in state S. What is the best action to do? That's the question. I'm not asking, oh, if you're in the current state S, tell me pi, because pi will also tell me in some these other states what to do. Okay, which I don't want to know, or which I don't want to know because first of all, it's going to be hard to compute other things. So where is this useful? Is useful in the case where you cannot plan everything beforehand. So when you solve the planning problem, when you said you solve for this pi, you have figured out you plan everything in advance in the sense that once somebody gives you pi, you just execute according to pi, right? In every state that you encounter, just look at pi. Pi says just take action A, take action A. So that's called planning everything beforehand. But forward search problem is just saying, oh, if you're in state S, what is the action to take? A, some A, action A. Okay, it's not asking for the object pi. So there's a difference between computing an object pi and finding a single best action to take in the current state S. Okay. So for Go, the forward search question is going to be just this: how good is the position S? Okay, and so let's ignore this for now. We're going to come back to this pretty soon. Um, so the way to solve forward search problem, I mean, although I'm kind of claiming that it's a very interesting problem, is the solution approach is very simple. Okay, the way you do it is because so remember this problem is just asking how good is the position S, as in there's a different question actually. What we need to figure out is what is the best thing to do now. Okay. To answer that question, you just what you do is you build a search tree from the current situation, current state, current board state, for example. You just find out, oh, what all things can happen. You know, from this situation, oh, maybe I'll, if I do these moves, I'll fail, I'll lose. If I do these other set of moves, I'll win. Okay, if you can kind of have a sense of these are the moves which will lead to wins, these are the moves which will lead to failures, then maybe you can assess what is the best thing to do now. Okay. Um, and so basically to do that you just solve a part of your mdp or your particularly just a part of your so wherever you are, that's the route, and from there you kind of just figure out what's the best thing to do essentially. Okay. uh, and the way you do it is, so just to recap, what is the forward search problem with this in this picture is that you are at state st and we're just asking what's the best action. Is it action a1, um, sorry, is it action one or is it action two? Okay, those are only two options. I just want to figure out what is the action, which of the two actions is good. Okay, and since I don't have a model. Okay, so um, um, I can, yeah, I can use RL style approach, which is that I can see, oh, I can take action two, okay, and it maybe I reach some state st plus one. From there, I don't know what actions take. Maybe I'll exhaustively take some actions. I'll maybe I took this action, went to some state, took this other action, terminated. Maybe in this case I won. Okay, if I won, maybe that's information that two is promising here. Okay, and but maybe I took something like this. Maybe, but at this point I went to some other state because of stochasticity and took some other action. Maybe again one. Okay, that reinforces that two is good. Okay, so all I'm saying is you just forward simulate what all can happen. Yeah.
It's loading the number of options.
Yes. Yes.
So
Yeah.
how do we limit that?
So we are exploring the number of options for now, and then we'll figure out how to do it more efficiently. If you don't, so okay, here's the thing, right? Here's the baseline. If you don't try out all the options, you don't know whether there's a game-winning move or not. Okay, so there's you have to try this, especially in the game of Go. There's nothing stochastic. Everything is deterministic, right? It's just that the game tree, in this case, the branching factor, if you think of it in terms of tree, it's so huge that you cannot really compute everything, and so there are some tricks to shrink it, and that's where reinforcement learning comes in. Um, yeah, so that was forward search using simulations where you are at some starting state st and you do some capital K number of simulations, which is basically in that state st you pick some way of taking decisions. You take decisions up to some terminal states, and then once you have these sequences of trajectories that are all possible from the state, take an average and see which one is a good move to do. Okay. um, there are a couple of variations. So if you take an average, if you take a simple average to figure out which move is good. So for example, if you have two options in the previous slide, there were two actions, right? One and two. Let's say you had 100 trajectories to compute. You try 50 trajectories for the first guy, 50 trajectories for the second guy, get an empirical estimate of for the 50 trajectories, how many times did I win using the first action? For the 50 trajectories, how many times did I win with the second action? Maybe 30, 30 out of 50 I won with the second action. 15 out of 50 I won with the first action. So you know which one is good. Okay, so that's simple Monte Carlo search. Okay, that's literally simple Monte Carlo search. Monte Carlo tree search is just going to be more efficient with the same budget, with the same 50 things that you can roll out, as in paths that you can trace out. How do you efficiently allocate budget so that you have a much better idea of, like, you can focus on the paths, trajectories, or paths which are more useful to you, so that you can assess the quality much better. Okay. Yeah, let me skip simple Monte Carlo tree search. I mean, that previous slide, but here's a picture, right? So as I said, in the game of Go, if you have a current position, okay, and in this case, white is playing, so white can play here, 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 Okay, here is, I don't know. So so I think here is just the value of the state, so it's not focused on specific actions, but whatever actions you can take. So white can place anywhere. Okay, so anywhere in this, anywhere at the cross sections, any of these cross sections. There are lots and lots of actions that you can take. But for every action, they're just unrolling what all can happen. Oh, if I put a white stone here, black will put a stone there. This is how ultimately the final board will look like. Maybe in this case, white one, capture some territory, or white lost, or something like that. So these are all the 100 executions that happened, out of which maybe two, in this case, four executions that happened, and two were led to white's victory. So the value of being in that state is 2 out of 4. Okay, but it can also be not just the value of the state, but you can also find the most promising action as well. Okay, which action is the one which is leading to victory versus not. Okay, so that's simple Monte Carlo search. Any questions about this part? Okay. So Monte Carlo tree search uh, is doing it in a different way. Okay. So as the name implies, it's gonna do this type of forward simulation, as in like try out a trajectory as well, but it's gonna do something directed at the beginning at least. Okay. By what do I mean by that? Okay, so let's say we are at a current state, which is this star here. Okay, so let's do one execution, randomly. At this point, we don't know anything, so we just do something random. Okay, maybe in this case, somehow we lucked out, we won, and so 1 out of 1 is the score. Okay, for now. So I'm going to draw a horizontal line. Okay, that's going to differentiate two different ways of unrolling. Ways of navigating through the path of that search tree. Okay, this part is some default policy. Think of it as random. Okay, in this part of the search tree, as in if I hit a state, some board position, from that board position, I'm going to do randomly, like finish the game. Okay, by simulating the other player and me simulating my actions, and so on. But in this part, I'll do something clever. Okay, and how is that? Um, so this first execution is something. Now let's say from this node, I have several options. Let's say I have two options. Okay, for simplicity, let's say I start with first option, which is put a piece somewhere. Okay, as place one. Okay, given putting that my stone at place one, and then executing the search tree, as in like do some simulation. I realize that I lost. Then I'm gonna put a value to this node here, which is a child of the starting node. I'm gonna put a value to that guy as well. So that's the first change. Okay. So I'm gonna start attributing values to the children. Okay, in that tree. Sorry, in that whole tree of possible paths that can happen from that current state. Okay, I'm going to start attributing numbers to the children. Okay, so children with numbers, those are going to be, I'm going to navigate around them using something called the tree policy, and then whenever there are nodes which have no numbers, there I'm going to just use the default policy. Think of this policy as random. Okay, so this is the same as before. This default policy should be like the regular Monte Carlo tree, regular Monte Carlo search. Just do something random default. Okay, it's just that there will be some nodes which for example, starting with the children of the source node, where I'll start attributing numbers. So for example, for this guy, right now the number is 0 out of 1 because there are 0 wins out of one thing that went through it. Okay, one path that went through it. Okay, let's try a second one. I have one more children, as in one more different action to take from the starting node. And it turns out that this guy is, never tried before, tried it, and it turned out it won. Okay, so then this guy gets a score of 1, 1. Now this part this is the tree, and there's going to be a tree policy here, which is that the next time I'm going to try to unroll, I'm going to prefer the star compared to the circle. Okay, so very very intuitive thing, right? I'm going to prefer the star, but At the same time, I'm going to be doing again exploration exploitation, which means that my exploitation information is that the star guy is a promising subtree to kind of figure out like what more rewards I can get, or is that really good or not. At the same time, the circle guy has only been explored once, so I should be trying the circle guy at least with small probability. Okay, so there's exploration exploitation, same thing that you have seen before can be done, except that now I'm attributing these numbers. You can call them actually q values if you want on some of these nodes. Okay, whenever I have that part is being governed by tree policy. Everything else is being governed using some default policy like randomly expand out the trajectory. Okay. Um, so here, because this was promising, this guy said, "Oh, let's go to this child and its child, and include that guy as part of the tree policy, and then from there do a random." Just found out you failed, and so now the scores get reflected everywhere. So now it's 1 out of 2 rather than 1 out of 1, but it still looks better than that guy. So now you're like, which option is good or not? Okay. So yeah, so that's essentially Monte Carlo tree search. So I don't want to go too much into details about MCTS, except that all it's trying to do is, if you have fixed budget of, let's say you can unroll 100 times, it's just trying to say those 100 times, let's say there are two actions at the top, action 1, action 2. Okay, it's just saying, oh, will you spend 50 rounds on first action, 50 rounds on the other action, to figure out action 1 is better than action 2 or not? Or do you want to actually, if you already know, like in 10 rounds that action 1 is not good, then maybe focus on action 2 to get a much better idea of promising directions, for example. Okay, for 2 actions, it's kind of not a big deal, but if you had lots of actions, which is the case in the game of Go, right? Then this makes sense. Okay, being judicious about how to split your budget of exploration. But at the end of the day, what are you answering? At the end of the day, you're just saying, at this position, what is the best move to make? What is the best placement of the stone? Okay, so that's what's written in text here. So I'm going to skip that. But so that's it. So that's Monte Carlo tree search, and actually we can play Go with just Monte Carlo tree search. Okay, except you can only play Go which are of really small size. Go boards which are small size. Okay, 5x5 or 7x7 or something like that. So the base idea for an agent to play Go is that at any given point of time, the agent has to figure out where to place its stone next, right? The other player could be human, for example. So to place the stone next, what it'll do is, it'll look at the board's state, go back to its dream world, where it starts with that board state as a starting route, and does this Monte Carlo tree search. Okay, maybe it has a time budget of 1 minute or 2 minutes. In those 1 or 2 minutes, how many ever paths it can do, it will do, in a judicious way. That's the tree search part. So as to figure out the most promising path, and therefore from that most promising path, what's the best action stone move that you can take. That is move it will do in the real world. Okay, but to do that simulation, AlphaGo at least did 2 variations. Okay, the 2 variations was essentially one to use what is called a policy network, and one is to use what is called a value network. Okay, so both this policy network or value network, just think of the functions. Okay, like a policy function and a value function. What are the objectives? What are the purpose? Their purpose is to let me do this MCTS operation efficient. That's all. This expansion operation that we saw, that we just need to make it efficient. So what is the policy network? It's a function which maps from board position to a distribution over where to place the next stone. Okay, so it's like, given the board position, which is 19 cross 19, with the configuration of where black is, where white is, to where should you place your next stone. Okay, so that's like whatever 19 cross 19 numbers, probabilities to predict. And a value network is saying, oh, given this board, what's the probability of winning? Okay, so that's one number to predict. Okay, so if you had those 2 functions, okay, you can kind of speed up the Monte Carlo tree search. Okay, here I'm just showing that network. So if you have this board position, you just want to produce a number like maybe you will win with probability 0.9. Okay, 90% chance of winning, for example. Okay. Similarly, if this is the board position, then best place to put your stone is maybe that location, for example. If you had the networks, okay, we'll figure out how to train the networks pretty soon. Um, so in fact, we'll probably not spend much time on training. So this is how it looked like. So there's a board state. Okay, I am the virtual agent. I need to explore this huge game tree. Okay, there's going to be so many moves, right? So at a given state, I can put white stone, in this case, the black stone at two different locations, right? So here and there are many other locations. So it could be 100 different stone locations, and at each location there's so much branching, right? So your value network does the following. Okay, so here's one Monte Carlo what is it called? Trajectory. Okay, so if I place white, if I place my black there, white will place somewhere else. I'll place black there, somewhere else. White will place somewhere else, all the way to who won, right? So one first, as I said, two extensions, right? First section here is the value network. Instead of going all the way to the end of the tree, after let's say 5 levels, you can just say, oh, after 5 levels, whatever the board state is, tell me what's the value of you winning. What's the probability of you winning? Okay, that's it. That's if you had access to such a nice function, then you don't have to really go all the way to the end. Okay, so that's first trick. And the second trick is that you don't have to follow, like just like we said, instead of maintaining numbers at every board state, you can actually have a policy network which will guide you to explore exploit in a more using a function approximation gadget rather than like you comparing numbers and then doing some explore exploit. Okay. So as well as you can use that same policy network to also run the forward simulation rather than using like a random default policy, for example. Okay, so those are the two extensions, and one last slide before we break is that I want to kind of focus on one third bonus thing, which is something called self play. Okay, so I want to tell you what self play is in 30 seconds. So by looking at boards and human moves, okay, so you have boards from which humans, we know, like given this board position, what did top rank, a human did, like a Dan 9 or some level person, what did they do? So you have boards and what moves, okay. So given that, you can actually figure out the policy network, right? Because policy is literally saying, given the board, what is the best move, what is the next good move to make, okay. So that's the supervised learning task. That's what they did. This is what they did in 2016. Actually, they removed the step subsequently. Actually, you don't have to even use human data at all. So that's this part. Now, what they did is they actually made two copies of their agent playing against each other. Okay, so it's like you had one policy network would be playing white, the other policy network would be playing black, and one would be kept fixed, and the other one would play and learn to improve itself. Okay, the network would improve itself. Okay, so that's the self play. That's what self play means, and it's very important new trick. I mean, not new trick actually. It's old, but kind of used effectively here. Um, and once you have the self play generated data, then from self play data they were training the value networks. But in the self play data, from this board position, they went all the way and won or lost. Okay, the one or loss is now the regression target here, and this board position is the input. So you train the value networks. Okay, so the non-trivial thing is, of course, train this guy, train that guy, and play agent against agent itself. Okay, like play an agent against previous versions of itself, basically, to so that you don't have to involve any humans to play. Okay, so that those are the tricks used in AlphaGo. Yeah, lots of CPUs, GPUs at that point. Um, to yeah. So any questions? So actually, next time we're gonna jump back to something else, which is structured data. So next time we'll look at graphical models and so on, which is a very different topic, but very interesting nonetheless. So if you have any questions, drop us an email or use the forum, or you can talk to me now. Okay.